And we already saw this GeoGebra applet where if I did, I can even pull it up again if we want to see it again. Here's the graph of the natural log of x. And if I take this point and I plot all of the slopes, there looks like there's two asymptotes, which there is. And this is half of the 1 over x graph. Why is it not all of the 1 over x graph? Well, the domain of natural log of x is just when x is bigger than or equal to 0. So the derivative is 1 over x. Technically, this is just when x is bigger than 0. Because you can't take the natural log of 0 or a negative number. So we've done questions like this before. No problem. 5 times 1 over x. So these first two questions are just a bit of review of doing logarithmic graphs, but now we might have chain rules. So we're going to figure out the derivative of this two different ways. Once, by using the chain rule twice, and secondly, by using our log laws to hopefully make it easier. And see which one you like better. Do you see that the x squared plus 2x plus 1 to the 1/3 is inside the natural log? And can you see that the x squared plus 2x plus 1 is inside the 1/3? This is why it's a chain rule twice. We have something inside of one function, and then that inside has something inside of it. So if you were doing the chain rule, you have to start with your outside function. Which is the outermost function in this case? The natural log. The derivative of natural log is 1 over x. So we would do 1 over, keep the inside the same. What was the inside? That x squared plus 2x plus 1 to the 1/3, which is another chain rule. What's the outside function now? The 1/3, the exponent. So that 1/3 would come out in front, subtract 1 from the exponent, keep the inside the same. And now the derivative of the inside is just 2x plus 2. Now, if you wanted to, we could do some simplification here. These have the same base. You could add those exponents together. But you wouldn't have to simplify. You could leave it as the first line. Or, the log laws are really nice. What can you do with that exponent? Bring it out in front. That reduces the amount of chain rules you have to do. Is there a log law for adding inside of a log? No. There's a log law for multiplying inside of a log. There's a log law for dividing inside of a log. But there is not a log law for adding inside of a log. If your log laws are mediocre, another thing we could do this weekend. Look at your log laws. Make sure you know them. Okay? They come up on our labs. That helps you review them. But they're going to come up a fair bit in questions here as well. So now when I do the derivative, I still have a chain rule, but only a chain rule once. because now the x squared plus 2x plus 1 is inside the natural log. I have a coefficient of 1/3. That just stays a coefficient of 1/3. And so I can do 1/3. Derivative of the outside function, keeping the inside the same, and then multiply by the derivative of the inside, which in its simplified form is exactly the same as the top one, but it's just a lot easier to work with, right? In this case, if you had used your log law. Both are right, but sometimes using one manipulation earlier can make it more simplified and easier to work with. So I think in this case, the second method is nicer. Find the derivative, and we have y's all over the place. That means this is going to be implicit differentiation. So we take d dx of everything. Do your derivatives like normal, but if you were doing a derivative with something with a y, then we add a dy dx, or a y prime. So here, derivative of 5y would be 5, but add the dy dx. The derivative of x squared, that's easy, that's just 2x. Derivative of natural log of xy is going to have a product rule inside, and it's a chain rule. So inside of the natural log, I have xy. So how do I do a chain rule? Well, I do derivative of the outside function, 1 over xy. Then I multiply by the derivative of the inside, and the derivative of the inside is a product rule. So I keep one the same, derivative of the second, then keep the second the same, derivative of the first. And then, of course, the derivative of 2 is 0. We have two places that you have a dy dx. Probably want to distribute this and then get my dy dx's on the same side. So I've distributed, move everything without a dy dx to the right, factor out that dy dx out of the two terms that have the dy dx, and then you can divide, multiply by the reciprocal, we were at 19 shortcuts. I don't feel very confident in that number, but someone can. And now we add the 20th shortcut. A log with any other base other than e. So far we've only been able to do one log, natural log of x. It's 1 over x. Now we're going to be able to do any base. And we actually need implicit differentiation for this. Because if you have y equals log base b of x, where b is any number that's allowed, which is positive numbers, x can't be 1, that's not allowed in logs. Or sorry, b can't be 1, not x. The base can't be 1. Because 1 to any exponent is just 1. It's not actually an exponential function. It's just a straight line. But if I have y equals log b of x, I could take that and change it to exponential form. And in exponential form, sorry, spelling mistake there. That's an A. In exponential form, I could do implicit differentiation of both sides. But you're going to have to tell me, do you remember what the derivative of b to the y is? It's the same as 5 to the y, 7 to the y, 3 to the y. Well, it's going to be, okay, so dd, this is going to be 1 on this side, and the derivative of an exponential function is always, stays the same, but then you add natural log of the base. And then because it's implicit differentiation and you have a y on that side, you would need a dy dx. If I want to get my dy dx by itself, I would have 1 over b to the y, natural log of b. And since b to the y is equal to x, I can take that b to the y and replace it with the x. Right? Remember that? Did you know that technically you could do this? Does that make sense? You could, if you wanted to, you could remember only one rule, that anything to the x is always e to the x natural log of it, and it just so happens that it works with e to the x, because what's the natural log of e?
1.
1. So technically, you could only remember that, but e to the x staying the same as e to the x is so easy to remember. Okay? We have just learned could we use this rule for a base of e? Yes. We could use this rule for a base of e too. If you wanted to only remember this log rule, you wouldn't have to memorize that the derivative of natural log is 1 over x. You could always write it as 1 over x natural log of e, but the natural log of e goes away and it just becomes 1 over x. But now we have learned our 20th shortcut. There's 20 of them. Challenge yourself on the weekend without making your list beforehand. Can you make all 20 of them without looking in your notes? If you miss one on the list, this is something that, I used for studying in high school and university. Whether it was math or psychology or history, I would break down important things in a unit and say, oh, there were 7 important things that you need to remember for the War of 1812. And I would just remember 7 important things for War of 1812. And then later I would say, can you list all 7? And if I could only list 4, it would mean that there were 3 things I actually hadn't learned yet. And I'd have to go back and be like, that's what I need to focus on. It's a good study strategy. You can use it in any subject matter. But then, if you can break down your items to, there are 7 things here, there are 5 things here, that is sort of a trigger for you to say, do I know those 5 things? If you know those 5 things in that moment, chances are you're going to know them on the test. If you don't know those 5 things in that moment, chances are you're not going to come up with all 5 of them on the test either. So there's 20 shortcuts for derivatives. That's a lot, right? But if you break them up, there's 12 with trigonometry. So now you're down to 8 other ones, right? I know so sometimes if you break things up that way, okay, I've got my 12 for trigonometry. Can I do all 12 of them? All 6 regulars and then all 6 inverses? And then there's e to the x ln x, 5 to the x, L log base b of x. There's another 4. So then you're like, okay, then what are the last 4 that I need to do? Product rule, quotient rule, chain rule. Now we're down to 1. And then the power rule. The easiest one is probably the one you forget, because at this point, we've done power rules so much. Does it almost seem like common sense? That's like, oh, derivative of 5x cubed. Oh, it's common sense. Bring 3 out, subtract 1 from the exponent. It's like kind of crazy that you have like some common sense calculus stuff going on already. Okay, so with that, one question to go. If y prime, find y prime, if y equals 2 log base 7 of x, well the 2 is just your coefficient, it would stay, and the derivative of log base 7 of x is going to be 1 over x, and have that extra natural log of 7 on the bottom. And all of our shortcuts are really important, because it's really easy for our brain to get mixed up once we start combining a bunch of rules together. And especially those inverses ones where you have like, I could do a secant inverse with a chain rule. There's multiple x's. All right, have a wonderful weekend.